Okay, so hello everyone and welcome back to the last lecture of parallel computing. So today I'm going to show you an end-to-end implementation of a distributed data parallel uh, algorithm for training a deep feed-forward neural network using Pytorch and MPI. So there are some prerequisites that you need to know. So if you don't know these concepts, it's good if you can review them or if you can learn it by yourself. So typically you need to know some basic concepts in machine learning, like supervised learning and let me just, okay, supervised learning and unsupervised learning, difference between classification and regression problems, model tuning and overfitting. Just let me check something here. Because I don't see the chat here. Okay. So some basic concepts from machine learning. Then you need to know some concepts from deep learning, like feed-forward neural networks, how you train a neural network using backpropagation algorithm. Then you need to know some optimization algorithms, such as the stochastic gradient descent, hyperparameter optimization, and model evaluation. Also could be helpful. And then from systems perspective, you need to know parallel and distributed computing concepts that you know already. Then you need to know some concepts about like high performance computing environments, like a Slurm, job submissions, things like that that we discussed in the workshop. It is also assumed that you are kind of familiar with deep learning frameworks such as Pytorch or TensorFlow. But we use these like deep learning frameworks only for tensor operations, algorithmic differentiation, and optimization. And finally, some knowledge of MPI or message passing interface is needed. And more importantly, I don't assume that you know about distributed training in machine learning because I'm gonna cover it like briefly in today's lecture. But it is good if you can deeply understand how this distributed training algorithm works in machine learning to fully understand what we are going to do today. Okay, so any questions about these prerequisites? All right.
Sorry, but could you upload the video about high performance computing, the recorded session?
Yeah, it is uploaded on YouTube, not on Moodle, so you can watch it
Oh,
there if you
okay.
want to. Yeah, I
Where
think
can
I
I find
uploaded
the
that
link?
last week or something.
Where can I find the link?
Uh, I think I sent it before in Moodle, so let me send it in the chat again. Just let me find it first. Okay, so it's on my YouTube channel. So and let me find the link. Okay, so I will put it here in the chat if you want to have access to.
Thank you.
But, I still don't find the chat. Oh, okay, sorry. Okay, you can also find previous lecture videos there as well. So not necessarily this workshop. Okay, so let's continue. So today in particular, we are going to train a neural network, a feed-forward neural network for solving a multi-class classification problem, which is a supervised learning task. And we will execute our program on a high-performance computing platform, in particular on Mahti. and we use Pytorch as our base for program, but we don't use Pytorch for distributed computation, but we use MPI or message passing interface for distributed implementation, and we solve a distributed training problem that I'm going to talk about now. Okay, so before seeing the actual implementation, let's talk a little bit about different parallelism strategies that you typically do when it comes to large machine learning projects. Well, there are different strategies. One of the most popular ones is called data parallelism or distributed data parallelism. Usually in the industry, when they refer to data parallelism, it means that you are performing your like parallel algorithm on a single machine. But when it comes to distributed data parallelism, it means that you are performing computations on different machines, right? Like a distributed computation. So in data parallelism, whether or not you're using a single node or like a multi-node system, what you typically do is to copy the whole model to each process or to each node. So in this case, by model, I mean a neural network. So you copy your neural network to each node, right? And each model, each copy of the model works on a different subset or different shard of the training data. So in data parallelism, you imagine that you have a huge data set that you really cannot fit it into a single machine. So you decompose your data set into different chunks or different shards, and then each node in your distributed computing environment will work on the same data set, but it tries to train a global model or a single model. So that's why you have this copy of the model in each node. If you look at it from centralized point of view, it is kind of training a one global model on the whole data set, right? But because you cannot really fit the data set on a single machine, so you want to do it distributedly. So that's why different machines work on different data shards, but training a single model, right? So and for this to be done, we need to do some sort of aggregation, because if we just train a model on a different data set, different shard of the data set, we will have multiple models. But we want to do some sort of aggregation to enforce that to enforce that we have a global model. Okay, so there are different strategies. Usually in the industry, they use the stochastic gradient descent algorithm as a standard and its variants. But in research and in research papers, you can find also different algorithms based on different optimization algorithms. So you typically have two strategies for this distributed data parallel machine learning. So the first one is synchronous stochastic gradient descent, where you have, as I mentioned, you have different copies of the model on different processes, as you can see here, right? But the processes, they perform some sort of all-reduce operation. In particular, here, as you can see, it is a ring all-reduce. So they perform an all-reduce operation to aggregate and average the gradients. So basically, each process has its own data, so they can compute local gradients, right? And then to aggregate the gradients, they perform an all-reduce operation to aggregate and average the gradient. And then they update the parameters based on this aggregated gradient. So this is a synchronous algorithm because you have to perform this all-reduce first. So all of the nodes should participate in all-reduce operation, and then they can update their parameters. So that's why it's called synchronous SGD. So this algorithm is implemented in Pytorch. So within this distributed data parallel module, and also in Horovod, which is a distributed computing platform used by TensorFlow, and it was originally developed by Uber. if I remember correctly. So at the core of this algorithm, you have this ring all reduce, where each process sends its data or a piece of the data to the next process and then applies the reduction operation at the same time. And then they do it in a ring, right? And they repeat this operation until all of the processes have access to the reduced gradient or average gradient, right? So this is one strategy. In the next strategy, which is called asynchronous stochastic gradient descent, again, you have different copies of the model on the workers, right? Like here. But instead of performing this all reduce operation, they push all of the nodes or workers, push the gradients to a central parameter server or a set of parameter servers. And in this parameter server, the gradients are aggregated, right? Because the gradients are sent to this parameter server by the nodes. By gradients, I mean local gradients, right? And in this parameter server, the gradients will be aggregated, like here, right? And then the model parameter will be updated. So you get a new weight for the model. And then the parameter server will like broadcast these weights to the workers. And then they can update the gradients based on the new weights, right? So in this kind of scenario, you don't need this synchronization because each node can fetch the weights if the weight was available. So they fetch the latest available weight from the parameter server. So they don't really need to wait until this operation is done, right? So this parameter server architecture is widely used by Google, and it is already implemented in TensorFlow. I will show you where you can find its paper and also the implementation. And this all reduce operation is implemented in Pytorch. Okay. There are a lot of details about these implementations, how you design a system like that and how you implement that, where you can find some of these details in the code and also in the seminal papers. Okay. So apart from data parallelism, you can have different parallelism strategies for distributed machine learning. So another one is called model parallelism, where instead of partitioning the data, you basically split the model across multiple devices. So for example, here we have a big neural network. Then you can assign each portion of this neural network to a machine for computations, right? You can assign the whole layer, or you can assign some tensors within a layer. So this is called model parallelism, and this model parallelism is usually used when you have a very big model, like a transformer models, where you have a quite big number of parameters, and you cannot really fit your model into a single GPU. But in the data parallelism, the assumption was that you cannot really fit your data into your machines, but you can actually fit your model in the GPUs within a machine. But in model parallelism, the assumption is that you cannot really fit your model in a single machine. So in an extreme case, if you cannot really fit your model and also cannot fit your data, so in this case, you should follow a kind of hybrid approach, which is obtained by combining data parallelism and model parallelism. Okay. And then we have this tensor parallelism, where you basically parallelize your matrix multiplication within a layer. So in this case, you can have a row-wise decomposition of your matrices or column-wise decomposition, and then you can use MPI or any other distributed computing platform to perform these row-wise and column-wise matrix multiplications. And you can see a small figure here. Okay. So this was a brief introduction to different distributed machine learning approaches. We can also find some other parallelism strategies, but data parallel and model parallel and the hybrid version of these are widely used by these deep learning frameworks and in the industry. Okay, so today we're gonna train a feed-forward neural network using a distributed data parallel approach. And in this case, we consider the neural network architecture to be like similar to this one, right? But not with the same number of neurons and number of layers. And we want to perform a multi-class classification task, right? So I imagine that you are already familiar with feed-forward neural networks, quite simple. So basically you have an input layer here, you have a set of hidden layers, and you have an output layer here. And you can obtain the value of these neurons, which here I call Z, by applying an activation function. So in this case, we are using ReLU activation to this matrix vector multiplication. And here, W's are our weights that we want to learn during this process. So for training a simple neural network in a centralized manner, you basically have a forward pass where you compute these values y1, y2, and y3, and then you construct your loss function, and then you compute the gradients in a backward pass using backpropagation, and then you update your weights according to a stochastic gradient descent algorithm. So I'm not going to talk about the details of training a neural network because you should be quite familiar with that process to understand the distributed version. Okay. So this is the network architecture that we consider for today's implementation. Okay, and in today's implementation, we implement a distributed data parallel training, and here I try to show you some sort of conceptual diagram on how you can do this conceptually. So we assume to have a big data set on a cloud, a store on a cloud database or something like that, and then we split the data into different chunks. So the data is you can have two scenarios. In the first scenario, the data is inherently distributed. So it means that the data is inherently stored like in different chunks. And in some other scenario, you want to you have a very like big storage system, and then you want to split the data into different chunks because in your nodes you don't have that big storage system, right? Then you send each chunk or each data shard to different nodes, typically on a GPU or a set of GPUs, right? Then you perform this forward pass on the local model that you have on that node, right? After the forward pass, you're going to be able to compute the loss function using the error that you define. So in this case, we use cross entropy loss because we are working on multi-class classification. And then each node will perform a backward pass to compute the gradient, right? And we have the same thing for other nodes as well. So here we also have a forward pass. This is another node. So these are different nodes. This is node 1. And this is node 2. Right? So on another node, we perform this forward pass on a different chunk of the data, and then we compute a local loss function, and then we perform this backward pass to compute the gradients, right? So up to this point, each node has its own gradient or local gradients, right? Here we have gradient 1, and here we have gradient 2, something like that. Then in this step, we should perform some sort of aggregation to combine these gradients into one gradient, and it can be shown mathematically that if we take the average of these gradients, then we can show that the algorithm actually will converge to a local optimum, local minimum. So in this case, here we perform this global, we perform this aggregation to compute the global gradient. So what was the operation that each node should perform here to calculate this global gradient? So anyone can answer me?
Should I repeat the same process?
Well, what was the name of the operation? Because here we need to aggregate the gradients, right? So in data parallel training, to aggregate the gradients, as I mentioned here, we have two strategies. One of them is this one, and another one is this parameter server, right? So in
Yes.
the first case, the operation that we do is all reduce operation. So here we do the same thing. We can also use this parameter server, but in this example, to show this all reduced distributed data parallel training, we use all reduce operation here to aggregate the gradients. Right? We talked about all reduce in the MPI lecture, actually.
Sorry, I have a question.
Yep.
How can we ensure that this distributed learning has the same output as the
Centralized one.
single node? Yeah.
Yeah, as I mentioned, these things should be shown mathematically. So I will talk about the distributed stochastic gradient descent algorithm in a minute, but if you have this if you take an average of the local gradients, then you can show mathematically that all of these local gradients, right, they converge finally to this to the aggregated one, right? And the aggregated one is actually the one that you compute on. And the aggregated gradient is the gradient that you would compute on the entire data set. Okay, so eventually you get into the centralized solution, but by performing distributed computations. Is that clear?
Are they exactly the same, or they are
Yes.
just local minimums?
No, they are exactly the same, but they will converge to a local minimum in terms of neural networks. But if you use a linear model like or with the convex loss function, they will also converge to a global minimum. So it depends also on the loss functional landscape as well. But typically, in terms of non-convex optimization, when you work with neural networks, if you solve the problem in a centralized manner or in a distributed manner, you eventually will get to the same solution, but with different number of iterations and different amount of time. So it depends on the algorithm as well, but theoretically you will get to the same solution. Okay.
Okay, thank you.
Yeah, in this case, mathematically, we call this a consensus. So we want to force a consensus between the nodes. So all of the nodes should agree on a solution, right? So when different nodes reach a consensus, then in that case we are basically having a centralized solution. So I will introduce some papers that you can read for understanding some mathematical details. Okay. So after you perform this R-reduce operation, you have an aggregated gradient, and then each node can update the local models using these aggregated gradients, and then you continue this procedure. Okay, so this distributed data parallel algorithm can be seen as like in optimization literature as distributed stochastic gradient descent algorithm with all reduced. And as I mentioned, algorithmically, you can also see what actually happens. So you have m machines. So this is the number of your nodes, right? Then you initialize like each machine with the random weight, right? Then you have your mini batches, like in typical stochastic gradient descent optimization, right? And then in this step, you need to compute your gradients. So this is the local gradient. And then you perform this R reduction operation, right? Which basically you need to average the gradients. So in this case, we sum up the gradients here, and then we divide it by the number of nodes here. But you can also ignore this m here and put it here. Okay. So in this step, we perform this R reduce operation to obtain an aggregated gradient, which is the average gradient. And then each node locally update its own model. And we continue that. Okay, so this R reduce operation, as I mentioned, has been implemented in Pytorch. So here in the left, you can see the seminal paper that they published to introduce this method in Pytorch. So you can have access to the paper here. And in the right, you can see the Pytorch documentation on this distributed data parallel implementation. So you can see the APIs here as well. All right. So let's talk briefly about the parameter server architecture. Again, for data parallelism. So here, as I mentioned, we have a parameter server, right? And each model or each node sends the local gradients to the parameter server, right? The parameter server will aggregate these gradients and compute the new weights, and then send the weights back to the nodes. And then the nodes can compute the gradient locally given this new weight. And this is the algorithm, as you can see. So you need a task scheduler, and then each worker, they load the data, and then they compute the gradients, and then they push the gradient to the server and also pull the weights from the server, right? And in the server, you aggregate the gradients, right? And you update the weights, and then the workers will get this weight from the server. Quite simple algorithm, but quite effective. So, and again, here in the left, you can
Sorry,
find, yep.
About the synchronous and asynchronous.
Yes.
I don't understand the difference. Don't the synchronous send back the weights to the worker, to the nodes?
No. In the synchronous version, which is this all reduce operation, here, all of the nodes must wait, right? So here you have a barrier or something like that within this all reduce. So all the nodes within your machine or all machines, they need to wait in this point until this all reduce operation is done, right? Because all of them should participate in this all reduce operation.
Mm-hmm.
But when it comes to asynchronous computation, you don't really need to wait all the time. So these nodes can get the weights from the server on their pace, right? So they don't really need to wait. You don't really need to have a synchronization here. So they don't really need to wait until the weight is updated on the server, and then they can get the latest available weight on the server to perform their computation.
I assume that the mathematics for this one is even more complicated.
Yes,
And does
usually
this
asynchronous
also
computation is more complicated than the synchronous one. Yes.
does this also converge to the one that
Yes.
is done by one? Okay.
Yes. Yes. It under some conditions, yes. And a good feature of this parameter server is, so it is kind of robust to node failure. So for example, if this node fails, then all other nodes can really work quite well. So and they can fetch their data, fetch the weight from the server. But in the reduce operation, if one node fails, right? Because all of the nodes should participate in the reduce operation, like here. If one node here fails, then the whole system will break down. So this parameter server is kind of robust to node failure, right? But essentially, it doesn't have the performance of this reduce operation. So it really depends on your needs. Okay. So the parameter server is implemented in TensorFlow. You can see the TensorFlow documentation here. And then in the left, you can see the seminal paper that they published, right? So if you are interested, you can read this paper. It provides a very good information on how these like distributed data parallel algorithms are basically implemented. Okay. So, we have about 15 minutes only. All right. So today I'm going to show you how you can implement this reduce distributed stochastic gradient descent. So we don't use Pytorch distributed data parallel module because I'm trying to teach you how to implement it yourself, and we do it using MPI for Py library, which is an MPI a Python wrapper around C++ MPI. So here we use Pytorch only for as a base for our distributed implementation for performing tensor operation and algorithmic differentiation, things like that. And we will train our model on Mahti CPU nodes just for saving time because GPU nodes take some time to allocate. But you can implement it, and you can use Mahti GPU nodes for experiments. Okay, can you see my desktop?
Yes, the GitHub page.
Yes. Okay, so here the code is available on my GitHub account, so you can find it in this distributed data parallel training repository. So I will put it also in the chat as well if you want to take a look. So it's here. So in this case, I'm trying to train this feedforward neural network on FashionMNIST dataset. So, and here is the paper that introduces this FashionMNIST. So I also put the link of the paper as well. So basically, this FashionMNIST is a like images of clothes, and then you have different classes like trousers, like dress, coat, and things like that. And then we want to perform some sort of image classification using our neural network on this FashionMNIST dataset. So if you want to be more familiar with this dataset, you should take a look at this paper. You see the paper, by the way, right?
Yep.
Okay, good. All right. So let's and there's another detail actually before getting the code in Mahti. So I think I didn't cover this in the HPC workshop, but when you work with these CSC supercomputers, you typically, after you logged into the system, you have access to 3 directory: home directory, a scratch directory, and APPL directory or project application directory, right? The home directory is a directory that you log into by default, and it has up to 10 gigabytes of like storage that you can use for configuration files, things like that. The scratch directory, which is available in this path, so /scratch and /your project ID, has 1 terabyte of disk space and it is used to store the program data. So if you have a data set, a big data set, or something like that, you should store it on this Scratch directory, right? So you should also read a little bit about what's the CSC policy on this and maintaining these like Scratch directories. For example, they will remove everything if you don't use your data within the first 180 days. And then you have this proj appl directory, which is about 50 gigabytes, and it is used for your project application. So you can have your code in this proj appl directory, your executables, your binaries, and everything. Okay, so the home directory is used for the configurations, a Scratch directory for your datasets, and proj appl directory for your actual code. So you should clone your GitHub repositories in this project appl directory. And something important is like these Scratch and project ppl directories, they belong to the project. So everybody within a project have access to these directories. So it's basically shared among the project members. So I have cloned this GitHub repository in this proj appl directory. So you should have access to this directory if you are a member of the project. And for the project, I use this, the project that I set up for the course, Parallel Programming, Oba Academy University, right? Okay, so now I try to log into Mahti and show you where you can find the actual implementation there. So as I showed you, you have to connect to your host, and then I choose Mahti here. Then you need to enter your password. All right, so I'm in Mahti now. So let me switch to ZSH. All right. So if you execute this pwd, now you are in, I'm in home directory, right? So now I have a question for you. How can I get my project ID so I can find my proj appl directory where the actual code is? Anyone remembers? If you remember, there was a command called csc-projects, right? And here you can find your projects. So for example, for this project, I have my project ID is project 2013968, right? So this would be the name of the directory within the Scratch and app and project application directory. So I just copy that. Then you click on open, and here you can see the entire file system. So here you just go to the root folder, you find this proj appl, and then you can see all the projects here. You don't have access to the projects of other people, but you can see the folders here. And then you need to specify your project with this ID. And here is our project. And if you open it, you can see a folder distributed data parallel training here. And then you click OK. All right. So now I am in this directory. So I have already cloned this repository here. And if you want to do it yourself, you just need to run git clone and the repository address here. All right. Okay, so this is the actual implementation that I try to walk through it. All right, so I start from the beginning. So First, you need to, if you want to debug your code in this login node, because we are now in the login node, so you should activate Pytorch Python environment. And how can I activate that? Do you remember? So if you remember, there is module, spider, Pytorch. There you can see different Pytorch versions, right? And then you can use module load, and then with the module name, right? But I don't load it here because I want to perform the computations on the compute node, or not on the login node. Okay. So now let's see how we can actually implement this distributed data parallel algorithm. So first, I just import Pytorch, so the torch module in Python. So these are not quite important now at the moment. Then I fix the random seed just for reproducibility. And here I provide a configuration dictionary where I can have different values for hyperparameters and some other things. So for example, the first one is for the epochs. This is the number of epochs that I consider in the training. The batch size, how much data I'm trying to process at the same time. The learning rate for the stochastic error descent algorithm, and the momentum. And here I try to specify the name of the directory where the actual data set, this FashionMNIST data set, is going to be downloaded to. So in this case, this FashionMNIST data set goes to Scratch, the project ID. This is the name of our folder, and this data, right? So if you want to see it, because I have already downloaded that here, so you just need to ls this directory. And if you do that, you can see that this FashionMNIST down here. Just let me clear my console. Okay. Right? So this is the FashionMNIST, and then you can go inside and see it. Okay. All right. So if you don't want to execute this code on Mahti, you want to execute it on your local machine, so you should make sure that make sure to change this path. So I try to write a comment here. Okay. Okay. So in Pytorch, you can use both CPUs and GPUs for matrix multiplication or tensor operations. So to check if GPU is available, you can use this. Just let me uncomment it here. You can use this torch.CUDA that is available function. So if if this function returns true, it means that you have like NVIDIA GPU and CUDA available on this machine. Otherwise, you should use CPU. So typically, when you want to work with Pytorch, you define a device, right? And then you kind of identify the device and select the device like that. So if it was available, you choose the device to be CUDA, and if it was not available, you choose it as a CPU. Because we need to wait a lot to get access to Mahti GPUs. So here I just comment out this line, and we will run everything on a CPU. But you can just comment here and choose this one, and then you can have your experiments on the GPU. Or you can rename this CPU to CUDA here, like that. Okay. So the next step is to create our architecture for this feedforward neural network. So for implementing that, you need to inherit from this NN module, NN.module from Pytorch. You can import NN for neural network from Torch. And then within this neural network module, you have an abstract class called called module. So basically in Pytorch, a module is a software component that takes a tensor as an input and returns a tensor as an output. So in this case, a neural network is a module, a loss function is a module, and you can find other things as a module. So this module class is provided by Pytorch to give you some flexibility to build your own different neural network architectures. Okay. Then I should initialize my feedforward NN, which is the name of my network. So first I need to initialize the parent class, easy. Then I provide a flatten, I create an object of the flatten class here, which basically, because in images you have two-dimensional data, and this flatten class will make it one-dimensional, right? So using this row-wise or row major data storage. And here I'm creating my layers. So first I need to specify this sequential, because I want to create different layers and then I want to connect them to each other. So it should be sequential for this purpose. Then I create a linear layer which has 784 inputs, because our images in this FashionMNIST dataset, they are 28 by 28 pixels, right? So then if you flatten this, then you have 784 like the elements or pixels. Okay. Then my first hidden layer has 128 neurons, and this is something that you can tune by yourself. I just put it here for simplicity. And then I apply a ReLU activation function for these hidden layers. After that, I create another linear layer. So the second layer. In this case, I have 128 inputs because I had 128 outputs in the first layer, and then 64 is the size of the neurons of the next layer. Then I apply ReLU again, and finally I come up with this linear layer, which has 64 inputs, which comes from the output of the previous layer, right here. And then I will have 10 output neurons because I have 10 classes in FashionMNIST dataset. So this is the structure of our neural network. Typically, you can basically do that as well. So you can have this linear, then 64 and 32 for more pre-processing. Then you can apply a ReLU again here. And then you have 32 to 10. So this would be 3 hidden layers, but because of the simplicity, we just continue with these 2 hidden layers. Okay. And then when it comes to Pytorch, you need to implement this forward pass function. And the forward pass function is basically computes the forward pass on the neural network. So you get an input, right? You flatten your input. So if it is 2D, you make it 1D. And then you send it through these layers that we defined here. So this input goes to the first layer, and then a ReLU activation function is applied, and then it goes to the second layer, and so on. So implementation of a simple neural network in Pytorch is as simple as this. So it's quite easy. Okay. So the next function that I defined is to load the data. So I want here in this function, I want to load the FashionMNIST dataset from Pytorch because they have it there. And then I want to partition this FashionMNIST dataset between different nodes, right? So let's see how we can do that. Okay, so the first thing that I do is to define a data pipeline for pre-processing. And you can have it using this transform.compose, and the transform module is available here in this Torch Vision library that you can install with Pytorch. So this compose basically composes different pre-processing uh, functions that you want, or pre-processing classes. So the first one is to tensor, because I want my image to be stored as Pytorch tensor. And then I have this normalize preprocessor. So anyone among you knows what this normalized preprocessor do? What does it do? Any ideas?
I don't know the module exactly, but the name probably suggests that it normalizes the values.
Yeah, it just what it does, the operation is you have your data, then you have to remove the mean, right? And then divide it by the standard deviation. Okay, so this is the mean of the pixels, and this is the standard deviation. You can compute it, or you can find it on the paper that I showed you, just to normalize the image, have everything between 0 and 1. Okay. So we just perform these simple pre-processings, and then we load this the FashionMNIST dataset, which is available in this datasets module. And you can also find this dataset module in Torch Vision as well. So here I load this dataset and download it to this config data dir, which is this scratch directory in Mahti, right? And then if you choose train to be true, it downloads the train dataset. Otherwise, it downloads the test one, the test dataset, right? So quite simple here. And then I load the test dataset, the test FashionMNIST. So here I just choose the train to be false. And I download it there in the same directory as well. Okay, so here, after I loaded the dataset, I want to split the dataset between different nodes. So this is an MPI application. So you know that in MPI application, this Python script is executed by each process or each node, right? So what I need to pass into this load data function is the rank, or the process ID, and the size, the total number of processes or the nodes that I want to use. So based on the rank and the size, I can partition the data. So first I get the total samples, the total number of data points, which in this FashionMNIST is 60,000. And then I divide it by the size, the number of processes to get the sample per rank, sample per process. Then I can see two cases here. I can evenly distribute the data here without any remainder, or I have some remainders, right? So I get the remainder in this case and I store it in this remainder variable. So I have the sample per rank, the number of samples per rank, and also how many samples I really cannot fit, like equally, that I have to, how can I divide the remainder also between the ranks? Okay. Then I create an indices variable to store the indices of all of the samples for this data partitioning. So I'm not going to explain this part in detail because I want you to think about it, but it's quite simple. So I will find a start index for each rank. So for example, if my rank is 0, so the start index would be 0, right? And if my rank is 1, the start index would be 1 times this sample per node. So it means that I'm choosing the start index blockwise. And here, this mean, rank, and remainder is used to basically like to basically divide the remaining samples equally into different nodes. So for example, if you have 10, let me write it here. So if you have 10 samples and you have 4 nodes, right? So you can have 8 samples stored in each node, right? But your remainder would be 2, right? So in this case, one of these samples is stored on the first node and another one is stored on the second node, right? So this is how you want to split the data into different nodes, considering that the dataset cannot be evenly distributed to different nodes. Okay, so it's quite simple. But I wanted you to know the strategy that I chose here, because you have multiple strategies. You can have, for example, these 2 remaining samples stored on only one node, and you can store it in different nodes. So in this kind of a strategy, depending on the remainder, right, you give each node only one sample. So in this case, node 1 and node 2 gets one of these remaining samples. So here I find the start index based on that. Then I have an extra if my rank is like smaller than the remainder, as I mentioned. Then I have the local samples. So you have the sample per rank plus that extra. Then you need to find the end index. And then you can find the local indices for that data, which is like the indices from the start index to the end index. Okay. And then you can use Pytorch subset class to get the training dataset and the index. So in this case, you pass in the training dataset, the one that you loaded
I
here.
think
Yes.
I think remainders are distributed based on rank. Each
Yes.
rank gets an extra one. It's not distributed evenly.
Well, it is not distributed evenly between all ranks. It is distributed evenly between the ranks smaller than this remainder, right?
Yeah.
So if remainder is 2, then you divide the remainder between the 2 first nodes. If it is 3, then you divide the remainder between the first 3 nodes, not all of them. Okay, so you use this subset. You can import it from Pytorch utils.data. So this subset class allows you to subsample your data. So you pass in your training dataset and then the local indices that you want, and then you can get a local dataset, which is a subsampled version of the entire dataset, right? And then I load the training dataset here. Data loader and the test data loader. So in PyTorch, the data loaders are used for for loading the data in different batches, not the entire dataset. So for example, for the trained loader, I choose the data loader to work with this local training dataset that I sampled here, which is the partition of the data. And then you specify the batch size using this configuration dictionary, and then you can shuffle the data there. And for the test loader, you can also create another data loader with the test dataset and with the batch size and other things. And finally, this function returns the train loader and the test loader. Okay, so just to recap, this load data function loads the data, partitions the data between nodes, and then creates data loaders and returns those data loaders for processing. All right. So I will explain this function later. So the next important function is the train function. And the train function is the function that implements the actual training algorithm. So you need to pass in the model that you want to train. Like in our case, it would be this neural network that we created. Then I pass the train loader and the test loader because I want to train and test at the same time. You need to pass in the optimizer, the criterion, which is the loss function, the rank of the process or machine, the size, which is the number of machines that you are considering, and this MPI com, which is equivalent to MPI com world in C that we saw before. So in Python, you can use this MPI com like that. So let's see how the training algorithm works. So the first thing that you need to do is to call this model.train because in Pytorch, Pytorch uses different strategies for model training and model evaluation internally. So you have to switch to train mode when you want to train the model. Then in the next step, I want to measure the wall clock time using MPI W time. We talked about that before. And here I provide a for loop on my epochs, right? So here I can get the number of epochs based on the configuration dictionary. And then I measure the epoch time. And I initialize my total loss function here. So quite simple. And then I will loop through the batches that this data loader provides for me. So in this case, I'm using the train loader because I want to use the training data, right? So in this case, the batch size is 64. So I get 64 samples and 64 target labels for my training. And this is the batch index, right? So in the next step, depending if I have GPU available, I need to move my data and my target to GPU or CPU. So in this case, you can use this device. So if the device is CPU, your data is available on the CPU, so it doesn't do anything specific. But if your device is GPU, then it moves your data to your GPU available to the node. So if you change the device variable to CUDA, then your data will be moved to your GPU if it was available. Otherwise, you will get an error. Then I will reset the optimizer gradients, just not to accumulate them. And in the next step, I perform the forward pass. So the forward pass is quite easy. You just need to call your model, which is here. You passed it as a parameter to this training function. You call your model on this data batch, right? So you perform the forward pass, you get the output, and then using the output and the target, which is your labels, you compute the loss function, right? So forward pass, computing the loss, and then you perform the backward to compute the gradients. So the backward is called on the loss function because you want to compute the gradients of the loss functions with respect to the weight. And here, backpropagation is wrong. So here you have the backprop. So up to this point, all of my nodes have access to the local gradients. So as I mentioned in the R-reduce stochastic gradient descent algorithm, so I need to synchronize the gradients now using this R-reduce, which is implemented in this synchronize gradient function here. So here in this synchronize gradient function, I get the model that I want to synchronize its parameters, right? Synchronize the gradients, the size, and the com for all reduce operation. So in the neural network, we have different weights, right? So which means that we have different parameters and we have different gradients with respect to those weights. So I loop through this model.parameters to get the weights, right? In case the gradient is not available, so I just ignore that iteration. Otherwise, I get the gradient, I move it to CPU because in this particular MPI implementation, my MPI is not CUDA aware. So if you want to move your data between nodes directly to GPUs, you should use a CUDA aware MPI. Just let me write it here. So because here we don't have CUDA aware MPI, so I need to move my data to CPU and then change it to NumPy format because OpenMPI works with NumPy in Python. So MPI for Py works with NumPy arrays. So you cannot really pass in tensors, Pytorch tensors here. Okay, and so I change it to NumPy, and then I call this RReduce function of this MPI comp, right? And then I divide this RReduce, which is the sum, by the number of processes. And then I replace the gradient of that particular parameter with the one that I calculated, with the aggregated one. So here. So now this parameter has access to the aggregated or the average gradient. Okay. And note that here, before this RReduce is done, you have an implicit barrier, something like com.barrier. So all the nodes within the communicator will wait here, and they perform the RReduce operation together. And then you can do the same thing for other parameters. So this is basically the logic behind this synchronized gradient function that implements this RReduce operation. So let's get back to the training part. So here you synchronize the gradients using RReduce. Then you optimize. You perform the next step in the optimization. So you update your weights based on the aggregated gradients. After that, so this is the basic training, but others are not really necessary. But I just wrote that here for completeness. So then you need to compute here I just compute the average loss for each epoch. So then I got the duration time for the epoch. Then I want to compute the global loss. So here I use another RReduce operation to compute the average of the local loss functions. So because each node has its own loss function, and then I wanted to compute the global loss function here. Then you should use this RReduce operation on the loss function to combine the losses of different nodes. And this line is not important because I got the parameters, the norm of the parameters. And here, in order to evaluate my model, I call this evaluate function, which is implemented here. So let's see how it works. So in the model evaluation function, I get the model, the test loader, the rank, size, and the communicator. I switch the model to evaluation mode, right? Then I use this Python context manager. It's better to say Pytorch. So in this context manager, basically, we are telling Pytorch not to compute the gradients because we just want to compute the output of the model. We don't need to perform this backward pass. So in this case, the computational graph that is created by Pytorch. So here it does not really capture the gradients. So basically, you don't have a computation graph here. It is just a tensor multiplication here because you don't need the gradient. And then again, I move my data to device if there was not there. and then I compute the model output. Then I compute the predictions. So to get the highest probability for my output classes, and then I count the correct predictions, and then I divide it by the total data to get the accuracy, right, in percentage. But this is only for some information along with the training. Okay, so let's get back to the training function. So I get the test accuracy here while I'm training, right? So if you see that in each epoch, after my epoch is finished, I get the test accuracy for that particular epoch. Okay, and here I just want to print some information. Because in MPI, every rank or every node has its own data. So I want to first combine all of these data to the root node, and then I will print a table in my root node. So this is the information that I want to print. So like the rank, the epoch, the test accuracy, average loss, all average loss, which is the total loss, and the epoch duration. So these are different in each node. Then I use all gather. As I use gather to basically stack this information into the root node. So we talked about the gather operation in the previous lecture. And then if my rank is 0, so if I am the root node, I will print this information as a table, right? So this is the table header, and then I print each row. And in this case, the row is this information. You will see the log files after it was done. And finally, I measure the training time, and then I use all reduce to report the maximum time taken by the nodes. And then I print it. And here it just for like performance evaluation purposes. You can read it by yourself, but I'm just saving different training time depending based on the number of processes, just for plotting purposes. This is useful for drawing this efficiency and speed of curves. And then I save my Pytorch model. Okay. So I think the most important part that was kind of different compared to the centralized case is this synchronized gradient and also this data splitting that I did here. All right, so now let's see what would be the main function that we call all of these functions. So first thing that I need to do is to set up my MPI. So I initialize my MPI COM word, and then I get the rank and get the size, similar to what we did in C. Then I call this load data function to get the train loader and test loader. Then I initialize my neural network here by creating an object from this feedforward NN that I created before. Then you need to specify the loss function, because here we are using this multi-class classification. So I define loss function to be this cross entropy loss. Anyone knows for logistic regression what kind of loss you should use? If you are familiar with that. It's called binary cross entropy loss. So if you only have two classes, not more than two classes, you should use this binary cross entropy here. Then I initialize my optimizer. So in this case, I'm using SGD. You can import it from torch.optim here. So this is a stochastic gradient descent, which is my local optimizer. Then you need to pass in the model parameters, the learning rate that comes from this configuration, dictionary, and the momentum. And you can also ignore the momentum. Then you need to move your model to the device, because you cannot really have your data, for example, on GPU, but your model on the CPU. So everything should be on the same device if you want to perform tensor operations. So I move my model to the device as well. And then I call this train function. And finally, I have my main. Okay. So I just need to now run this main.py file on Mahti using a Slurm by submitting it to a queuing system. All right. So let's see how I can have this JavaScript here. So this is my JavaScript to submit this. By the way, let me open CSC console here in the right, just to show you the status of the job. So let me log in into Mahti first. So as I said, Mahti uses two-factor authentication. So you should have one of these authenticator applications also. All right, then I just click on jobs to see the active jobs and just put it here, direct. Okay, so this is my JavaScript. So as we talked about in the workshop, so you need to have a name for your job. You need to specify the project ID that you can get using CSC-projects. Here I am allocating 20 nodes on Mahti, and number of tasks per node is 1, which means that each node only needs to run this main.py. So you don't have multiple processes within a node to run this main.py. So only one process, and each process can have up to 32 threads using this CPU per task. And then I allocated 1 GB of memory per CPU. So in this case, I have on each node, I will have 22 GB of memory. Then 2 hours maximum execution time. The partition that I choose is the medium partition because I want to use 20 nodes. And then I want the output of my program to be stored in this FashionMNIST output.txt file. Okay, so because it's a Python program and I want to use Pytorch, so you need to load Pytorch and also MPI, like these modules on the compute nodes. So otherwise, the compute nodes do not find these packages that you use, like the Pytorch package. These ones are not found if you don't load the Pytorch modules there. And then you should also load OpenMPI to make sure that MPI and MPI for Py, the Python wrapper, is available. Then you can run this srun and then to execute your code using this python.main.py here. Okay. All right, so now let's submit this job if it works. So what was the command for submitting a job on Mahti? Anyone remembers? It was S what?
srun.
S-batch. Right? This srun is for running the code, but if you want to submit it into the queue, you should use this s-batch and then followed by this run the bash script. So I just submitted it to Slurm, and here in the right, if you refresh this page, you have a job here that is submitted. So it is in the queue now, and then you can use this watch queue to see the status of your job. So at the moment, my job is pending because Slurm is trying to allocate some resources for that. You can also refresh here, see the updates. So I hope it is run until we end the class, but let's wait a couple of minutes. So it's still pending. Okay, but in the meantime, because I ran this code before, so I have this FashionMNIST output.txt file here that I can show you. So this is basically the output file that this program generates. Let me refresh again. No, it's in the queue again. All right, so in this case, we allocated 20 nodes. So this is what our program prints to the console. So for example, rank 6, which is the sixth node, has 3,000 samples, and this is the indices of those samples. Or rank 14 also has 3,000 samples. So in this case, we could distribute the data among nodes evenly because we have 60,000 samples and 20 nodes. So each node gets 3,000. So my rank should start from 0. So I have the 0 one, right? Up to 19. So 20 nodes uh, are working on this problem. So this is just some information that I printed when the data partition was done. And here is a table that I designed during the training. So in this table, you can have the rank, the epoch, the test accuracy, the local loss, total loss, and the time taken by each epoch. So for example, rank 0, so all of them, because of the all reduce operation, they perform the same test accuracy because they have the same models basically, because they are updating their models based on the same gradient, which was the aggregated gradient. So this is the first epoch and the information of all ranks. This is the 10th epoch, epoch 10. Then your accuracy is 84. Then you have the 20, the epoch 20, your accuracy is 86. And I think I ran it for 50 epochs, so, or 40, but it was 50, I guess, but it was not printed here. Or let me see the number of epochs here. Yeah, it is 50, yes. So then finally you get the final accuracy on the test data set of 87.93%. So, and the maximum time taken by this program by all nodes was 103 seconds. So you can also have your own experiments. You can change these hyperparameters like the number of epochs, the batch size, and the learning rate, the momentum, and everything to see what accuracy you can get, and also you can test it using like GPUs, not necessarily CPUs. But you can see even in the CPU case, it's taking some time to allocate the resources. So everything is in the queue at the moment. Okay, so it depends really on the usage on Mahti. Okay, so you can get access to this code as I mentioned on GitHub, and also if you navigate to this directory, this one. So proj appl, and then the project ID, and this distributed data parallel training. Okay, so is there any question? All right, good. So let me first stop the recording here.